let us take to today's portion also, just to have a general idea what will be targeted for alkenes, dienes, and alkynes. Now see, there is dienes also. So we have to go for physical property, boiling point, density, dipole moments again, preparation by elimination reactions, acid catalyzed hydration, metal acetylides, reaction of alkenes with KMNO4, ozone, reduction of alkenes and alkynes, electrophilic addition reaction of alkenes with X2, HX, HOX, effect of peroxide on addition reactions, and cyclic polymerization reaction. Okay, in this total, yes, we will try to do the conjugate additions discussion wherever there is possible. I will try to discuss the conjugate additions discussion. Okay, so let us start in this sequence, plus minus here and there. So of course, the general introduction for alkenes and alkynes is, general formula of alkenes is CnH2n, alkynes CnH2n minus 2. They both are unsaturated compounds. Yesterday we have clearly discussed degree of unsaturation is different and unsaturated compound hona is different. So here they are having both degree of unsaturation as well as our unsaturated compound. Bond dissociation energy is C triple bond. C is 823 kilojoules per mole. C double bond C is 681. And C single bond C is 348 kilojoules per mole. Right? So 348 to 681 to 823. Total BD of all the three bonds in case of alkynes is highest. Then comes the double bond. Then comes the single bond. Bond length is, for alkynes, it is 120 picometer. For alkenes, it is 133 picometer. Single bond is 154. Carbon hydrogen bond dissociation energy also you need to have an idea, have to have a little order setting. See, C single bond is 348 kilojoules and C single bond H is 435.8 kilojoules per mole. So it is quite high. And when we are talking of bond dissociation energy word, it is always the homolytic bond fission that we are considering by this method. Coming to physical properties of alkenes, C1 to C3 gas at room temperature, C4 and C17 are liquids, and again higher are waxy solids. As yesterday also I said that they are not strong solids, they are soft solids. Okay, they are not tough solids. Ethene has faint sweet smell. All others are odorless and colorless. Boiling point increases with increase in molecular weight. Roughly, I can say, with every CH2 group increased, boiling point increases by 20 to 30 Kelvin. This is a rough estimate, need not to be exact. Somewhere around this is what I can tell, that with every CH2 group increase, you have a boiling point increase of 20 to 30 Kelvin. Okay, like alkanes, for isomeric alkenes with increase in branching, boiling point decreases. Same yesterday we discussed for alkanes, how with branching the boiling point will go down. Okay, they are insoluble in water but soluble in non-polar solvents like ether, benzene, etc. Okay, now see here, this was discussion of physical properties of alkenes. Now I am moving to alkynes. So I would rather say same as alkanes, same as alkenes and alkanes. Okay, it has a pretty much similar behavior like alkanes and alkenes. What that the first three members are gases, next 8 are liquids, and higher are solids. First 3 are gases, then there were liquids, but the liquid range was C4 to C17, which was more than 8. Here it is next 8 are liquids, and then they begin to solidify. Of course, again, soft solids. Ethyne has smell, all other are colorless and odorless. Similar in the case of ethene, you had ethene, alkene, you had ethene has faint, sweet smell. All other are colorless and odorless. Same thing. They are slightly polar as compared to alkanes and alkenes. Yes, because percentage S is increased, polarity will increase. Their melting point, boiling point, and density will increase with increase in molecular weight. That is one general factor which will be observed. Now let us start with preparation of alkenes, how to prepare alkenes. This particular starting, this page that is on your screen is extremely important. There are almost every year, either of this will be in exam, be it mains, be in advance. I'm not saying the entire question will be based on these two, but they will be important part of the entire question, somewhere maybe in the sequence, maybe entire question concept, but these are important two reactions on your screen. By partial reduction of alkynes. Yesterday we did a complete reduction of alkynes and alkenes to alkanes. Then we wanted full reduction, complete reduction. But what if I want to stop at alkene? I have two choices. First, by the metal hydrogen wise combination. Yesterday we were talking of Raney nickel. Raney nickel was something that was becoming a stronger or a better reducing agent. Okay, palladium barium sulfate, Lindlar's catalyst. So it was a stronger reducing reagent. Rather, I should say more activated catalyst, Raney nickel. Okay, so in that we were targeting small amount of catalyst, doing complete reduction till the end. Here we are just doing the opposite of what we were doing yesterday. We are decreasing the efficiency of the catalyst by adding something called poison. Now, what is poison here? Barium sulfate is acting as a poison on the surface of palladium, because this entire hydrogenation functions on the capacity of the catalyst, how it allows the adsorption of alkene or alkyne like this. Then we observe that a bond breaks and it forms a bond with surface of metal. Similarly, there is hydrogen which is getting absorbed and this bond gets weakened and then they get added. So if this surface is pure, is available more, the catalyst efficiency is high. But if this surface is not effective or is poisoned, is decreased by sprinkling over something which itself is not reacting with our alkene or hydrogen, but is indirectly hindering the reaction. So palladium poisoned by barium sulfate, this thing is done. Okay, so they do the poisoning thing by barium sulfate, Lindlar's catalyst, and we get cis alkene, that the hydrogens are, as yesterday we discussed, this is a syn addition. So on alkene, if I do syn addition, cis alkene is formed. Okay, so cis alkene once formed. Whereas if I want to make trans alkene, then there is a very important different reaction called Birch reduction. In Birch reduction, what we do is we take sodium in liquid ammonia. Okay, we take sodium in liquid ammonia. Now this sodium in liquid ammonia do the anti-addition of hydrogen, opposite side. With Lindlar's reagent, syn addition of hydrogen takes place. So cis isomer is obtained. Okay, whereas here complete things are again returned. Lindlar's reagent is partially deactivated. Palladium carbon, palladized charcoal. Poisoning is done by barium sulfate, sulfur, or quinoline. Quinoline structure is this. And this is how it is written in NCERT. I want you to read this parallelly because what language they have used. See, alkynes on partial reduction with calculated amount of dihydrogen in the presence of palladized charcoal. Okay, partially deactivated with poisons like sulfur compounds like sulfur BSO4 or quinone give alkenes. Partially deactivated palladized charcoal is called Lindlar's catalyst. Alkenes thus obtained are having cis geometry. However, alkynes on reduction with sodium in liquid ammonia form trans. Now, they are not mentioning the name here of this birch and all, but they have mentioned that, okay, sodium in liquid ammonia give trans. So, we have to discuss it all. Here, it should be clearly mentioned BaSO4. Otherwise, you will see that palladium carbon and you get direct alkene only. No, barium sulfate is there. Everywhere they have to add barium sulfate on these arrows. Is that clear? Now coming to this birch, sodium in liquid ammonia, how does that work? See, as in S block, you must be aware of sodium when dissolved in liquid ammonia is always a source of solvated electron. Electrons are there which are dissolved in liquid ammonia. Okay. Now this electron adds to alkynes. So if I see homolytic fission and you add one electron, it becomes radical anion. Now these radical anion is definitely unstable. There is no doubt about that. Now this radical anion has two possibilities, either exist in a cis arrangement or in a trans arrangement. So this is unstable because ultimately this anion and radical are electrons. They will definitely repel each other. So they want to stay opposite of each other. So more stable arrangement is this. Okay, and less is this. So this is like formed in negligible or zero amount towards tending to zero. And this is formed major. So what happened now? This anion dissolved in ammonia is the condition. So ammonia gives H. And you have radical. Again one electron, again anion, again ammonia gives proton. And finally, we have overall anti-addition of hydrogen and transalkene is formed. Okay. Now, if I start again adding one more electron, then this bond rotation is now allowed. And as a result, the repulsion between this radical and anion will be more because they can rotate, and the average out repulsion between radical and anion is higher, causing unstable nature of this radical anion. This is destabilized by this, and so alkenes are not reduced by birch to alkanes normally. Okay, birch will not reduce alkenes to alkanes. As yesterday also, no, not yesterday, as this question appeared on this concept. Okay, see, if I check, this one is chiral. And here they have given alkyne. This is alkene, cis. Hydrogenation of the above compound in the presence of poison palladium catalyst. So what will be the product formed if I take a poisoned catalyst? Let us draw. I think the product will be one double bond will be left and a triple bond is gone. So we expect that we will get this. And if this, now you see this center is now a chiral because both the sides cis and cis bonds will be there. Okay, I could have drawn it a little more better, like same identical. All of you agree to that? That yes, this is correct. This is the cis geometry of this particular bond. As a result, this center is now a chiral. So what we get is an optically active compound? No. An optically inactive compound? Yes, we got an optically inactive compound. Racemic mixture, diastereomer? No. So answer is B. And a similar concept, question have been asked on these concepts. If I talk of mains 18, 20, 21, 22, in fact 24, 25 also, and in advanced 2019, 21, 22, and so on. Okay, so this hydrogenations, controlled hydrogenation by Lindlar's catalyst to cis-alkene and by Birch to trans-alkene is to be remembered. Talking more of Birch. Remember, Birch fails to reduce alkenes to alkenes. Fails to reduce terminal alkynes to alkenes also. Terminal alkynes to alkenes also. Why? Because there will be acid-base reaction taking place. Okay. Now, based on this, see, we can expect a question like this, that as we said that Birch fails to reduce terminal alkynes, what if I am given CH3CH2 CHO plus RC triple bond CH, and on arrow they give sodium in liquid ammonia and ask what will be the product form. Okay, so I will say that the product form is organometallic path because the terminal alkynes will form RC triple bond CNA, and this is acting as a Grignard organometallic. So CH3 CH2 CHO plus RC triple bond CNA. This is what will be observed. CH3 CH2 CHONA C triple bond CR. This will be our answer, not the reduction. Okay, so for terminal alkynes, organometallic formation with liberation of hydrogen gas is observed. In case of conjugated dienes, how does that work? Now see, in case of normal alkenes, I said that this radical anion formed is very close and repulsive. Whereas if it is conjugated, it can have 1 and 4 position, like this resonance, right? Here it is 1 and here it is 4th. So by resonance, this is formed. Okay, and then this one's formed. Again, to have the maximum distance minimum repulsion objective, it will have a anti-position transposition arrangement, and therefore you have trans-alkene formed, trans-2-butene. Instead of just saying 2-butene formed, I will say it is a trans-2-butene formed. Okay, similar thing here can be observed, but definitely this is going to be a conjugated carbonyl. So first we get this, and then it tautomerizes to aldehyde, right? So we get from conjugated carbonyl to aldehyde. It appears that the alkene is reduced in the process. So yes, it was a 1,4 addition, and thereby alkene is reduced in this process. Clear? Next, we go for Birch reduction of benzene. Now, benzene, when we talk of a metal hydrogen reduction, it is very difficult to stop anywhere in between for metal hydrogen. It will go to cyclohexane, nothing in between. Whereas with Birch, we get partial reduction and we get this type of diene to be formed. So it is important that if I want to stop the reaction at diene stage, I have to use Birch reduction for the purpose. Instead of metal hydrogen reduction, we will use Birch reduction. Clear? Going further, preparation of alkenes by elimination reaction. What if we want to reduce by elimination reaction? Right? So if I want to reduce by elimination reaction, I have so many methods. So we can prepare alkene by elimination reactions, starting from alkyl halide or alcohol. We can do elimination from any of these. For example, first, let me start. What are the elimination reactions? It is a beta elimination for alkene formation if I'm talking, or 1,2 elimination reaction. Okay. So these beta elimination reactions could be like E1, E2, even CB, EI or EC. These are my examples of beta elimination. Beta elimination, when see the two groups which are being released are placed adjacent at alpha beta positions or 1-2 position in the original substrate, then it is called beta elimination, E1, E2, E1, CB, EI or EC. Clear? Now E1. E1 is unimolecular elimination reaction. One is unimolecular, E is elimination. Now, when I say unimolecular, the general points I hope all of you must be aware. RDS is carbocation formation. And then the H is lost, right? L is the leaving group. Rate equation is rate directly proportional to CH3, CH2L. Rate will increase with increase in stability of carbocation, yes. With increase in leaving group nature of L, rate of reaction will increase. Faster this group will leave, faster the reaction will be observed. With increase in solvent polarity, rate will increase because the species involved are ionic. Therefore, more polar solvents, faster and better this RDS will be. As complete carbocation is involved, so you will definitely have rearrangement of carbocation in the reaction. You will observe the rearrangement of carbocation. Regioselectivity, if in a reaction two possible positional isomers are formed but only one is obtained as major, then the reaction is called regioselective reaction. See, regio यानी region, selection of region, that is called regioselectivity. And now regioisomers कौन से होते हैं? Regioisomers are positional isomers. So if there is a possibility of more than one positional isomers to be formed, but the reaction is selecting some specific, then it is called regioselective reaction. Okay, you can have a Sedzeff elimination or Huffman elimination. Sedzeff elimination, beta H is removed from more substituted carbon. Huffman, when beta H is removed from less substituted. These two terms, I guess you are comfortable with. So minus HL, removing this, I have Huffman and Sedzeff product. In even reaction, Sedzeff products are the major products. If two geometrical isomers are formed in the product, the trans isomer is obtained as major. Please remember, regioselectivity we have done. Now, amongst the Sedzeff itself, if I have a choice of geometrical isomers to be obtained, and there is a possibility that yes, it can exist as a cis and trans thing, then in even trans isomer will be obtained as a major. For example, if I talk of D or L of 2-butanol, dextro and levo isomer of 2-butanol, and take concentrated H2SO4 heat, okay, then see what we are having. Minor is 1 in, major is 2 in. Out of these also, if I talk, yield of trans 2-butene is more than cis 2-butene, and lastly it is 1-butene. Reaction would be 2 or more steps, because like in basic even I have said 2 steps, but in this it could be more because protonation also there, na? And right, so we have to take care, like dehydration of alcohol. If I take example, see, first there is a protonation of alcohol, then removal of carbocation is next step, removal of water forming carbocation is step 2. This is RDS where carbocation is formed. This is RDS, and from here H plus is removed and we have got all these products. Now see, it is a 3-step. If we are asked number of intermediates in a reaction in a step, then it is equal to 1 and 2. Then it is equals to number of steps minus 1. And if you are asked number of transition state, then it is equals to number of steps. Okay, for transition state, it is number of steps 1, 2, and 3. And for intermediate is number of steps minus 1, 1 and 2. Okay, so as I was saying that reaction would be 2 or more step, minimum 2 step for E1, Could be more, and could be more example is dehydration of alcohol. Okay, I took intentionally 2-butanol, not 1-butanol or anything else, right? Byproduct of this is ether by SN1. Yes, once carbocation is there, alcohol is there. So alcohol can attack on this carbocation like this. And you can have ether also as form. Always SN1 competes with E1. That is a fixed trend. High temperatures will support elimination. Otherwise, you will have major dominance of SN1 reaction rather than E1 reaction. We have to have high temperature for elimination reaction because eliminations are ultimately endothermic reactions. You have to break 2 sigmas, and against that you are forming 1 pi. So it is endothermic reaction. CH3, CH2OH. So this is ethanol, smallest possible, and also primary. So see how highly concentrated H2SO4 is required, and temperatures are 170 degree to 180 degree centigrade. At lower temperature, ethers are major product. I'll have diethyl ether as a major product if I keep the temperature lower than this. And this particular thing we are trying to follow from NCRT. Okay, we have to take this zest from NCRT, and I'm taking that content again from NCRT portion, just for your reference that what exactly I'm looking for and what I want you to remember. Let me reach to the exact place. How the NCRT has written. Yes, here it is. Yes, you can see it now, right? So they have written dehydration. See, this is what I was referring. Ethanol, H2SO4, 443 Kelvin. Okay, so roughly around 170 to 180 degrees centigrade. This is what I was referring to. Moving to 2 degree alcohol, 85% H3PO4, and temperature is brought down. So that is what we also did, right? We have also brought down the temperature 120 to 140 and roughly 60 to 70, whereas they are clearly mentioning we should have this thing 85% H3PO4 and H2SO4 could be 60 to 70%. Is that absolutely clear? I will add here or 85% H3PO4. Acidic strength will also decide how much we want. Okay, see 20% H3PO4. Now here H2SO4 is also similar or 20% H3PO4. 85 to 90 degrees centigrade. See the degrees, almost of 100 degrees in the requirement of temperature. Okay, that is how it is considered that easier to form a carbocation, better or faster the E1 will take place. Thus, the relative ease of dehydration is tertiary, secondary, and then comes the primary. Mechanism is certainly same, like this, formation of carbocation. Though I have a strong objection to what is written here in NCRT, right? Ethanol will not go by E1. They have formed a complete carbocation and taken it forward and did not bother to write anything about E1, E2 here. Okay, they have just shown the mechanism of ethanol with full carbocation. Tertiary carbocations are more stable and therefore are easier to form than secondary and primary. Tertiary alcohols are the easiest to dehydrate. That is all they have mentioned. But when we talk of our detailed process, what happens is dehydration of primary alcohols is basically E2 reaction. It gives us impression of E1 due to rearrangement of carbocation, but actually it is E2 followed by addition of H plus and then again elimination. What I want to say, if it is a primary alcohol, it goes by E2. This full carbocation is not formed. But as alkene is formed and it is prone to attack of H plus, we will again have a carbocation. Now, once this will form a carbocation, competition between 1 degree and 2 degree, 2 degree will form as a major. And we get what we were assuming, that how a 1 degree carbocation will shift to 2 degree. It is not a shifting, it is E2 followed by addition. Products are same as E1. Okay, so that is the confusing point, but the exact thing is for primary alcohols, it should be E2 followed by addition. Absolutely okay. For 2 degree and 3 degree, go by pure E2, by pure E1, but for 1 degree, go by E2 followed by addition. We can use H2SO4 or H3PO4 for dehydration by this method. We cannot use HX. Why? Because these HX, these X minus are conjugate base of HX and they are also good nucleophile. For example, Cl minus, Br minus, I minus. And thus they are also poor base because HX is a strong acid. So instead of elimination, substitution will dominate and Rx will be formed. Okay, instead of elimination, we'll have substitution. Whereas with H2SO4, H3PO4, the conjugate base formed are poor base, as well as they are poor nucleophile. So we'll have even products dominating. We cannot use oxidizing acids like HNO3, HClO4, etc. because they can cause oxidation of alcohols. That also we cannot. Okay, E2 mechanism, yes, alkenes can be prepared by E2. You take base, most stable is the anti-periplanar transition state for ZZF product. Alkenes are formed. That is fine. Okay, single alkene is here considered anti-periplanar. Rate is K into alkyl halide or any substrate multiplied by base. It could be again one or more steps. It depends on what is the leaving group. For example, if it is alcohol, definitely more steps. OH is not a good leaving group. We have to convert it to H2O, then only it is a leaving group. So it depends. Okay, concerted because there is a simultaneous bond formation and bond breakage involved. Simultaneous bond formation, see base, simultaneous bond formation of this double bond. Bond breakage, carbon, hydrogen and carbon L bonds are broken. As it is endothermic because it is elimination. So I can have single step ke liye I can draw this type of energy diagram. The ZZF transition state is more stable. So usually ZZF products are major products. But with bulky base, okay, or with bad leaving groups, we can get Hoffman products. This is specific. Either you have to have a bulky base, like tertiary butoxide. Okay, if I take this, then despite the fact that the ZZF, S is ZZF, the H to be removed is forming a ZZF product. If I take this, yes, I would have had a better alkene. But the thing is, due to bulky size of base, it is difficult for it to approach a more substituted site and therefore it fails to attack here and attacks here. So we get Hoffman alkene as a major product. It could be chlorine, bromine or iodine with alcoholic KH, small size base, or I can say even other small size base like NaNH2, you will have ZZF alkene form. Clear? Dehalogenation is also an E2 reaction. RCHX, CHX, zinc. Then it is also an E2 reaction. Okay, that is also an elimination reaction in which RCHZNX organometallic like woods, you can say. This is formed. Yesterday we were doing intramolecular woods like that. So NT elimination, the two groups will be placed NT, Zn, X2 is removed. So this is also an E2 reaction. Clear? Alcoholic KOH, base is OH minus, but is less solvated as compared in water. Never ever consider that in alcoholic KOH, there is something called RO minus. This is a wrong understanding by several students that if we talk of alcohol and NaOH, then we get RO minus as a base. No, this is not what is being used because this is a negligibly forward reaction. RO minus will not be formed because alcohol versus water. Water is a strong acid. So the reaction will not go to this direction. This will go to back direction. Okay, weaker acid and base. So this is negligible and is not sufficient to initiate or to do the reaction. So never consider that when we talk of alcoholic NaOH, the base is RO minus. The base is less solvated OH minus. So this is sterically hindered and we have done what is to be discussed there. Important. With fluorine. See, here I mentioned chlorine, bromine and iodine. This is steric and all factors and Setzeff-Hoffman. With fluorine, as it is a bad leaving group, irrespective of the steric of base, whether I use alcoholic KOH or I use tertiary butoxide, I end up forming Hoffman alkene. Okay, for same alkyl, E2 is, the E2 is order is Ri, then RBr, then RCl, and very difficult for RF due to high bond dissociation energy of RF. ठीक? Rate of E2 will increase with increase in leaving group nature, that is fine. It is an anti-elimination. The groups to be removed has to be placed NT in the exact conformation, not in the fissure. This is fissure. Don't get confused that it has to be placed NT here. Here, wherever it is placed, you have to, ideally, you have to rotate it in conformation, exact 3D. In the NT position, that is what is meant by NT elimination. The two groups to be removed are placed opposite to each other. Yes, for fissure, you can have a direct shorthand. If the two groups which are to be removed are either, okay, both on the horizontal line, whether they are on the same side of this horizontal line, I mean, same side of vertical line or opposite side of the vertical line, it doesn't matter because in fissure, both these are ultimately directed towards you. Okay, so it doesn't matter. This is not NT. This is simply same side they are placed. So you shorthand is you remove them, write whatever you are getting HET, MED same way, and then reverse for your answering. What is the reverse? H and Me were on the same side. So I just interchange Me and D. Like now H and Me are on opposite side. So answer is this. As I said, whether they are on the same side of vertical line or opposite doesn't matter because this is not the actual 3D structure. So here also you have to do the same thing, interchange and give the answer. Okay. Yes, but if these two groups were on one vertical and one horizontal, then you can go by the same answer. No need to do the interchange. Okay, that is the shorthand. If they are both on horizontal or both on vertical, then you have to opposite or give the interchange answer. If one is horizontal, one is vertical, then whatever you are getting is the final answer. You can go by that. E2 reactions show kinetic isotope effect. Now, what is kinetic isotope effect? With use of heavier mass of isotope, okay, I have to give more bond dissociation energy to break that bond. More BD required, it means it is difficult and rate goes down. So Here we want to say that CH3CH2X, then my beta hydrogen is H, proton. Whereas here my beta placed isotope to be removed is deuterium. But as bond dissociation energy of CD bond is greater than CH bond, therefore rate of E2 for CD3CH2X is less than CH3CH2X, and this is called kinetic isotope effect. That is, with change of isotope, there is effect on kinetics of the reaction. Is that clear? This again an important point, that if I talk of vicinal or geminal dihalide, and now if I remove 2 moles of HX, I can form alkynes. But what reagent I should take? If I take alcoholic KOH, now out of these two, alcoholic KOH base is OH minus, NNH2 base is NH2 minus. So out of these two, NH2 minus is a stronger base. Okay, so whatever alcoholic KOH is doing, NNH2 will automatically do. There is no issue. And so, but any of these I take, I remove 1 HX. This way or that way doesn't matter. 1 HX. Here I remove 1 HX. I get a vinyl halide. Now this vinyl halide will be difficult for me to vinyl halide. For this, it is difficult for me to go for E2. Why? Because now this bond X is in resonance with this pi bond. High bond dissociation energy of this CX. Similarly, with increase in percentage S, carbon-hydrogen bond energy is also increased. So now to remove 1 more HX from vinyl halide, the reaction is difficult. So to overcome that difficulty, either I need a stronger base, which could be NNH2, or you need high temperatures with the same poor base. Alcoholic KOH, 200 degrees centigrade or more. You can use temperature at least 200 degrees centigrade or more. Then you can find that yes, second step dehydrohalogenation is possible. Otherwise, it will fail. Absolutely clear. Now, if you have a terminal alkyne, which are acidic, this H is acidic, and I'm using NNH2. So I will end up further acid-base reaction. I'll not have this as my answer. I'll have this sodium acetylide as an answer, which can be used for SN2 reactions further and enlarging the chain of the parent alkyne. Ka is in the order. This is not a possible reaction with alcoholic KOH because water is stronger acid than ammonia, then no problem. Okay, water is stronger acid than ammonia, and then ammonia versus terminal alkyne. If I talk, I should rather write water is strong, then it is terminal alkyne, and then it is ammonia. This is the order of K. So when we talk of basicity, order become HO minus is weakest, then is the RC triple bond C minus, and then the NH2 minus. So NH2 minus being the strongest base, therefore this reaction takes place. Whereas with NaOH, this reaction will not take place. Okay, with NaOH, KOH, this reaction is not taking place, only with NNH2. So be very, very well informed regarding this. Dehalogenation is also E2. Same logic you have to do. Remove the 2 halogens if they are on the horizontal line and are either on the same side or opposite side of vertical line, doesn't matter. Remove them, draw alkene, and report the answer as opposite. That is fixed. For Fischer, that is fixed. For cyclic systems, E2 is extremely specific about anti-elimination. It may compromise between Sedzev and Hoffman choices. That is allowed, but between NT and SYN, it will never compromise. Okay. Is that clear? Correct? That only and only E2 will take place when the groups to be eliminating are NT. Yes, out of those, if you have a choice of Setzeff-Hoffman, you select Setzeff over Hoffman. See here, bromine is here, so I have anti-hydrogen here also and anti-hydrogen here also. This is giving me Hoffman product, right? This is giving me Hoffman product. This is giving me Setzeff product, but I have anti-hydrogen for both. So I'll remove this H and we'll have Setzeff as certainly major we are talking, not the sole product. There will be some Hoffman which will be minor. Okay. There will be certainly some Hoffman products. This side obtained CH3, H and CH3. This is our Hoffman product and this will be minor. So if given a choice, selection agar hame karna hai between Setzeff-Hoffman, that is possible. But sin elimination, I will never have elimination from this side. That is for sure. To prove my point, I took this. Here I got two products, major and minor. Now here if I talk, this is Hoffman, very good. But I will have zero other side product. This bromine, this is the H for Hoffman. There is no anti-H for Setzeff. So Hoffman, and I'll write as sole product, not as a major or minor product. Okay, so I hope I have made my point very clear that if you need to compare between Setzeff and Hoffman, there is a choice. But for NT elimination, there is nothing like a minor sin elimination must be taking place. That is not a possibility. Okay. Special methods for preparation of hydrocarbon from metal carbides. This is a direct factual inorganic sources we are using. Calcium acetylide, you will have acetylene. Magnesium propylide, if I use, then I will have propine. Al4C3, then methane. B2C, methane. This is one extra information I want to add, that calcium oxide plus carbon. At very high temperature, you have CaC2. This CaC2 we are using here. Okay, calcium acetylide hydrolysis to acetylene is commercially important in those welding acetylene flame apparatus or instruments. There we use this reaction. Okay, there we use this reaction. I lost the track. I am here. Okay. So all these methods are used for preparation of hydrocarbons. Though if I talk of only these two are alkynes, I am aware of the fact, but I want you to revise these two also. That with Al4C3 you will have methane, with Be2C you will have methane. Is that clear? ठीक. Let us move further. Next portion पे जाते. Chemical properties of alkenes and alkynes. That was the major preparation. Let me once check all preparations we have covered. What we have covered? We have covered physical properties, boiling point, density is always, they are always lighter than water. That is fixed. Dipole moments, cis and trans dipole moment they are talking, which was covered in isomerism, I guess. Preparation by elimination reaction, acid catalyzed hydration. Also here they are starting the reactions. So we have covered preparation by elimination reaction. Till here we are done. Now we are moving to this part of the chapter. Correct, we are on track. Let me go to, so chemical properties of alkenes and alkynes. Electrophilic addition reaction is what they will show because they are pi electron dense systems, right? So general electrophilic addition, first we'll study that HA is there. A will attack at a more substituted carbon or a less substituted carbon. More substituted carbon is called a Markovnikov product and is major. Less substituted carbon attached is anti-Markovnikov product and is minor. Now, what is the mechanism? So, alkenes are attacked by HA carbocation, which is 2 degree, and then attacked by A minus, 1 degree, then attacked by A minus. Okay, and please note this also, as a new chiral center is obtained but through sp2 intermediate, so it will be obtained as racemic mixture. Okay, RDS is carbocation formation, so rate increases with increase in carbocation stability. For example, if you are asked for different alkenes, what will be the relative order of addition of HBr, ozone, even ozone? Ozone also follows the same order as HBr. Or any electrophilic addition, if questioned, just form the carbocations from them and compare the stabilities. Better the carbocation involved, you say ease is more, easy to have this addition product. AE on alkenes is faster than on alkynes. Again, because if I go for alkyne, I will have an unstable carbocation formed, right? If I go for alkyne, RC triple bond CH, even for 2 degree if I talk, I will have an unstable vinyl carbocation involved. Vinyl carbocation is unstable. Okay, as compared to this normal alkyl carbocation. So alkenes are faster to go for electrophilic additions rather than alkynes. Regioselectivity, yes, again, Markovnikov products are obtained as major products. Rearrangement of carbocation if full carbocation is observed. But remember, in alkynes, vinyl carbocations do not rearrange. Okay, vinyl carbocations never rearrange. So you will have rearrangement of carbocation, but that is of a normal alkyl. Alkenes के case में valid है point. If any chiral center is generated, it will be obtained as racemic mixture. Correct? Now see what all reactions ideally you should know. I have made this a summarized chart. So you should know addition of dilute H2SO4, which will form alcohol. Addition of HBr, normal HBr, HCl, HI, all I want to intend here. HX is what I want. Markovnikov addition, 2 degree positions will be attacked. HBr in H2O2, that is Kharash effect or peroxide effect, you should know. Bromine in CCl4. Now this point can be used in POC because brown color bromine will be decolorized. So it is a test of unsaturation of alkenes and alkynes. Chlorine in water, you will have halohydrate forms. HOCl, same as chlorine in water. Interhalogen compound, then take I positive Cl minus and add Markovnikov. Hot concentrated H2SO4 is alkenes combining with another alkene that we'll see. This is one more reaction you should know. Then comes these 3 very important reaction in the last. B2H6 in THF followed by NaHH2O2 is HBO, hydroboration oxidation. Mercuric acetate followed by NaBH4 is OMDM and the ozonolysis. So if I go addition of water, I'll skip those which are very obvious, okay, and will mainly concentrate on the last 3. But I'll try to just brush the basics. So if I have this type of alkene, the difference between the 3 methods of forming alcohol from alkene are summarized in this. Dilute H2SO4 will have the rearrangement of carbocation and Markovnikov. So it is Markovnikov with rearrangement. Okay. If I go by HBO, hydroboration oxidation, I'll have anti-Markovnikov without rearrangement. If I go by OMDM, oxymercuration, demercuration, I'll have Markovnikov but without rearrangement. See, this is how we have a complete spectrum of converting alkenes to alcohols using different methods. If alkynes were used, then in dilute H2SO4 and OMDM, ketone is formed. And in HBO, aldehyde is formed with rearrangement in all 3. Oh, sorry, without rearrangement in all three I should have written without rearrangement in all three. Okay, HBO में aldehyde for terminal alkynes, not for all. Okay, so in alkyne, if alkynes were used, then in dilute H2SO4 OMTM, ketone is formed always, whether you take terminal or non-terminal. In HBO, aldehyde for terminal alkynes and keto for non-terminal. Okay, without rearrangement in all three. Alkynes में there is no rearrangement. This is another, like dilute H2SO4, you don't take direct dilute H2SO4 addition. You have to have a catalyst. Otherwise, the vinyl carbocation is not stable. So you have HgSO4 के presence में water addition that will tautomerize and you have a ketone formed. Coming to addition of HX, HBr, HCl. These are the normal Marconic additions with rearrangement. Only HBr shows peroxide effect. HCl in peroxide, even if you take, then also it is Marconic addition with rearrangement and through carbocation. That is interesting. With peroxide HBr, anti-Marconic addition through radical. Only HBr shows Kharash effect, no other. Again, if I talk for alkynes, addition of HX, gem dihalides are formed. This is again an important point. I hope all of you have this in your memory that with alkynes, first I had HX, I got this. Now if I see HX further one more addition, my choices would have been this two, na? Either vicinal or geminal. But gem dihalides are formed major and this is minor. Yes, why? Because if I talk of this addition on vinyl halide, okay, if we talk of addition on vinyl halide, let me explain this point here. If I talk of addition on vinyl halide, which was RCX double bond CH2, if I want to add further HX, my choices would have been formation of this type of carbocation or formation of this type of carbocation, right? These both are unstable. I should write here. Let me write it as 1 and 2. Both are unstable as compared to RCH plus CH3 if this X is H, because of electron withdrawing nature of X. So they are both unstable as compared to this alkyl carbocation. Okay. But अब इनमें भी अगर हम करें, there are two bad cases, but if compared order of stability is RC, I should write down, RCH plus CH3 is best, then it is RCX plus CH3 and then it is RCHX CH3 CH2 plus. Why? Because here only minus I of X is used. Here minus I and plus R of X is used. So yes, net it is withdrawing, but some amount it is returning with its plus R nature. So out of the two bad situations, we are selecting the one which is relatively less bad, which is this. Okay. Therefore, one is formed as major. And if one is formed as major, so RCXCH3 plus is major, then X minus will attack on it. RCX2CH3 is formed as major. As major, resulting in gem dihalides. Is that absolutely clear? That with alkynes, you will have gem dihalides formed like this. Okay. With alkenes, it is okay. And one also important point you have seen is with peroxide, only HBr will show kinetic isotope effect, not HCl or any other like HI. And they will continue to be carbocationic and Markovnikov products to be major. Addition of halogens or HX or X2 in water. For them, we have a intermediate called cyclic halonium. This cyclic halonium is an example of non-classical carbocation. Okay, this cyclic halonium is an example of non-classical carbocation. Classical carbocation, where it behaves like a carbocation, but the plus charge is on some other atom than carbon, then it is non-classical carbocation. So what we have is this halogen is involved. Now see, carbons are from the second period, but this halogen is from the third period. So this overall, this cyclic halonium is not uniformly bonded with these both sides. Okay, one of the bond, say A bond or say the B bond, is going to be weaker. Now what is found is A bond is weaker than B, because when system has to select which bond to be weakened, then it will select the one where the plus charge, if generated, is relatively handled easily, is relatively stabilized. So this is a 2 degree. So even if I have this bond a little weaker, R will do the plus I. So 2 degree will have a more higher del plus nature than this 1 degree. Now on this, if I have X minus, this will attack from this side because this is already crowded. So halogen is from one side and the X minus from opposite. That is why you will always have NT addition for these three. Whether you talk of X minus attack, you talk of water attack, or you talk of alcohol. Whatever after this halonium is attacked will be attacked from opposite side. Okay, and overall you will see the products are Markovnikov because the negative part is going to more substituted carbon. Okay, vicinal dihalide, halohydrins, these are called halohydrins. Okay, and this is ether and halogen combination is formed. If there is any other nucleophile in the medium, most welcome, anyone can attack here. Rearrangement are absent because it is not that a free carbocation is involved. So there won't be any rearrangement. Okay, there won't be any rearrangement. There would be just attack by this method, but no rearrangement. Markovnikov products will be there. And a very important reaction, ozone-lysis. I hope all of you remember, if it is zinc, water, or H2S. First is ozone, then the reagent given for breaking that ozonide is zinc plus water, or you can have zinc plus H2S. Then, or simply H2S will also do. You will have this type of fission. The net reaction is best. Break the bond, put double bond O. If you want to go back, just place the products in a way that the two oxygens are approaching each other. Remove them, extend the double bond, and you will get the parent. That is the big fix approach we want. Okay, so if it is a ketone and aldehyde combination, very good. If it is a ketone-ketone, you can have cyclic systems, then you will have same carbon in the product, otherwise the carbon in the product will decrease. If zinc is absent, then aldehyde will be oxidized to acid. If zinc is present, then you will have aldehyde and ketone. If it is a diene, okay, even benzene undergoes ozonolysis, and in fact, this ozonolysis method for benzene is one of the evidence that it has a 3-pi bond. Okay, there is this type of bonding. Same thing, alkenes, terminal alkene, I have formaldehyde. Conjugated, I have glyoxal. And allenes is there. Then central one is having CO2. Okay. Alkynes, ideally alkynes ozonolysis is nowhere. But if question, and nowhere I mean no good book referred to this ozonolysis in detail. Okay, but in our internal exam we can expect, so just remove these two bonds and form double bond. If it is terminal, form formic acid and carboxylic acid. You have to break this totally. But do not convert formic acid to any further. Stop your answer to formic acid. Okay. Oxidation of alkenes and alkynes can be done by use of acidic or alkaline cheminophore. Now, one more thing I'd like to add. Particularly, be very cautious for this particular orthoxylene. Okay. If we are asked ozonolysis product for this, ozonolysis products, then particularly as it is given in NCERT, yes, it is aromatic. For other xylenes, this benzene resonance doesn't have much impact. But for orthoxylene, you have to consider all the RS as a localized structures, and then you give the products. See, for this, if I take, my answers will be, and then CHO, and then 1 mole of glyoxal. Okay, I'll report CHO. This is what from this. If we talk from this, then I have to add one more this structure, right? And then 2 moles of glyoxal. So, but by any chance, if you take only one structure at a time, you may miss out on a particular option in there. So please take, particularly for orthoxylene, both the resonating structures separately, and then you formulate your answer. Okay. With meta and paraxylene, whether you do this or not doesn't matter. It gives the same answer. But with orthoxylene, it is different answer. So be careful. Oxidation of alkenes and alkynes, very easy oxidation if you have alkaline cheminophore or acidic cheminophore. Then to just break them and convert to acid. Okay, alkaline cheminophore heat given, acidic cheminophore heat given, or hot concentrated K2CR2O7 conditions, then break. But if you are given cold dilute alkaline cheminophore, then it is called Bayer's reagent, and you have controlled oxidation to vicinal diol. Okay, you have products which is you can call glycols are formed. Vicinal diols are glycol. Here we have to maintain that this cheminophore should be absolutely dilutest possible. Let us go in NCERT what they have written. Oxidation of alcohols, they have mentioned. This is, sorry, I have to go for 11th NCERT. This is 12th. Let me open 11th NCERT, because there they will give you how to report oxidation product is what I want exactly, so that you make no errors. This is alkanes portion. Yesterday we did this. All of pyrolysis, confirmations. done. Coming to alkenes. Okay, see how they are giving the bond angle and all. You have to keep notice of all these structures also, because anytime they can ask question from these structures. Isomerization is not what we are looking for now. But yes, the dipole moment if considered, boiling point, see. Just go through NCERT reading once, wherever you get a chance. Okay. Dipole moment. Between 0.33 dBi, whereas trans is given to be 0. So coming to preparations, we have done from alkyl halide and all constituents, 4 physical properties we have done. And this is every CH2 group, there is increase of 20 to 30 Kelvin we have done. Addition of dihydrogen, halogen, Markovnikov. These portions we have done. I'm looking for particularly oxidation, addition of sulfuric acid, addition of water, oxidation. This I want. Okay. What is their language? Need to be very careful. Alkenes on reaction with cold dilute aqueous solution of potassium permanganate. They are not mentioning the concentration. Usually we say less than 1% is best. But NCERT is not giving. They are simply saying cold dilute aqueous solution of potassium permanganate is Bayer's reagent, produce vicinal glycols. Decolorization of KMNO4 solution is used as a test of unsaturation. Fine. Okay, and see the temperature, 273 Kelvin, 0 degree per, they are using this reagent. Okay, acidic potassium permanganate or acidic potassium dichromate oxidizes alkenes to ketones or acids, because if it is aldehyde, it will be acid, depending upon the nature of alkene and experimental conditions. Okay, so that is a confirmation that nothing more they are mentioning. But of course, I have to add acidic KMNO4 or acidic K2Cr2O7. Any of these will give you RCOH, acid. So coming to this again, if alkynes are subjected to same way, break them, form acids. With Bayer's, they will form RCOCOR. Now, decolorization of Bayer's reagent. So this is used as POC. POC, test for unsaturation. The decolorization of Bayer's reagent can be used as a test of unsaturation. Right? Now here, if these are alkynes, these are terminals, right? Like this, or here this. Then with this particularly, this terminal CH2, which could form formic acid, but KMNO4 also oxidizes formic acid. So that is why we are saying CO2 will always be formed. Okay. Next, let's go to allylic halogenation, use of NBS or bromine. And 2 years back, 3 years back, we had a detailed integer on NBS in JEE. NBS, N-bromosuccinamide, we use with traces of HBr, small amount of HBr. So it is basically function of NBS is to provide Br2 only, nothing more. Okay, the basic function of NBS is to provide Br2. And then it is normal halogenation of alkane series, that bromine in presence of sunlight or heat forming Br radical, and we are proceeding to stable radical involved allylic bromination. It is a radical reaction, and as allylic radical is more stable than 2 degree, NBS ka function is gradual and continuous source of bromine. That is its function. So it is formed preferably. How many products will be formed? This was the question. Okay. In actual, what was there? We have to check first. I have to check this answer also. May or may not be appropriate. Let us do it. So what is your approach? Always form the radicals. How many allylic positions are there? So my first allylic position is this. So I'll form the radical. I'll consider its resonance. And with this resonance considered, I will draw the product. So if I take a radical here, I'll have this product. If I have the resonating structure, I have this product. Correct? These are my 2 products. Coming to next. This is my second position of radical, this. And it has two resonating structures. So I'll draw. From this position, I'm getting bromine. And it is chiral, right? So wedge and dash, two cases will be obtained. From here, I will again have chiral center. So two centers from here also are involved. Now I will see what are my choices if I get this place as a radical, then what will be the case. So for third one, let me draw. I will have this as a radical and its resonating structure will be this. Agreed? They both are like similar, but still I can have different products. So let me check. I will write this is my product. Do I have a similar product elsewhere? No, I don't see any such products formed before. And this is also chiral. If I draw another for this one, it will be same. So I'm not drawing those. Any of these will ultimately giving this. And I think this will give me two products, right? So how many products I have got? 8 plus 1, 9. So answer for this should be 9. All of you also check. So what should be the approach? You draw the possible sites of radical like this. Draw their resonating components. What are the possibilities? Like these are the resonance structures. So total 3 radical sites, and then use their resonance and then draw the products. And finally, after drawing, you check how many GI/OI are possible. That is the best way. Okay. Polymerization reaction, linear polymerization, Ziegler-Natta catalyst. We have so many famous polymers. Polythene, Ziegler-Natta catalyst is Et3Al and TiCl4. Alkynes, you have polyacetylene. It conducts electricity. Please take a note of alkyne polymerization also, because it may get neglected otherwise. See, polymerization of alkenes is very common. Polythene and all, you know that how it is formed and everything. It is famous, right? But alkynes, suddenly their polymerization is just like neglected. Let me go to alkynes here. Chemical properties, of course, their acidity we have seen, addition reactions, addition of water, dihydrogen, halogen. See, in alkynes, they are not referring to ozonlysis. Okay, they don't give ozonlysis in alkynes in NCERT. That is what I said, ki no good author has referred. But in linear polymerization of alkynes, under suitable condition, linear polymerization of ethine takes place to produce polyacetylene or polyethine, which is a high molecular weight polyene containing these units and can be represented like this. Under special condition, these polymers conduct electricity. And uska use dekho. Thin film of polyacetylene can be used as electrodes in batteries. These films are good conductors, lighter and cheaper than the metal conductors. So this is something, you know, the cyclic polymerization. You know this type of ethene polymerization, but linear polymerization of acetylene is also important. Take a note. Okay, it conducts electricity. Other polymerization is Cu2Cl2 and NH4Cl. Then you have a vinyl acetylene formed. Let me add a little more. If you add HCl to this, then we get this product, which is chloroprene. And chloroprene is a monomer of isoprene rubber. So if I make a polymer of this, then I get iso. Oh, no, don't add the word isoprene. Isoprene is a natural rubber monomer. Then we get a rubber as a polymer. And it is called neoprene. The rubber is called neoprene. Okay, so this is important. Acetylene, Cu2Cl2NH4Cl. We have this vinyl acetylene, HCl, chloroprene, and then neoprene is formed. Okay? Cyclic polymerization is quite famous. I hope all of you remember this, but still, acetylene, you have a benzene. Red hot iron tube, if you have 4 moles of acetylene, cyclooctatetraene. Propine, then you have this mesitylene. Okay. If I have 4 acetylene and the catalyst is NiCN2, then you have again cyclooctatetraene. Okay. POC, practical organic chemistry of alkene and alkyne, decolorization of bromine water, decolorization of Bayer's reagent, light color, pink color is decolorized. Terminal alkynes have these acidic H reactions like NNH2, then ammonia liberation, Grignard, methane, NH, hydrogen liberation reactions. They also form precipitate with these AgNO3 or Tollens reagent. Now, it will not give a silver mirror test, but it will give a white precipitate of silver alkyl light with terminal alkynes. Cu2Cl2, copper acetylide, which is explosive and is of red color, red precipitate. Acidic nature of terminal alkynes, we have already discussed with NNH2, it will form sodium alkyl light, which is nucleophile. Of course, with terminal alkynes, you have to remember N factor will become 2. So if some integer is referred, how many moles of ammonia is liberated or how many moles of, if Grignard, then how many moles of alkane is formed. Then you have to see that whether it is a terminal alkyne with only 1 H or it is acetylene with 2 H. That could be a point of concern. Okay. Now, we have done the basics. Now, we are coming to conjugate additions, reaction with conjugated dienes, 1,2 or 1,4 addition. See, this is my conjugated diene. Okay. If I talk 1,2 addition, then just, this is not specifically IUPAC positioning I am referring because it depends bigger molecule, how it is, just as basic, then 2 halo product is obtained. This is called 1,2 addition, only position 1,2 involved. Whereas this is 1,4 addition involved. Okay. What is the mechanism? So we add HX. RDS is carbocation formation. It is resonating. These are not 2 different carbocation. It is the same carbocation. Okay. It is not different. Now, this is not formed at all. 1 degree carbocation without resonance, there is such a different energy barrier. So this is not formed. We have to talk only this. Allyl 2 degree carbocation is formed. It has 2 resonating structure, 1 and 2. If we talk of stability, 1 is more stable than 2 because it is 2 degree. Right? Now, if 1, I form the product, then I get the product 3. If I form product from 2, then I have a product 4. Okay. If I talk of product stability between 3 and 4, 4 being more hyperconjugative is more stable than 3. So 4 is more stable than 3. 1 will have more contribution in the resonance hybrid, more hyperconjugation for double bond in 4. Now there is a problem. 1 which is more stable as an intermediate is producing 3. And the one which is less stable contributor is producing 4. Okay. So what happens? See, the first step is same. Now the transition state for 1,4 product is having a high barrier, but the product is stable. Transition state for 1,2 having a less barrier, but unstable product. See, transition states like this. So this is more stabilized, na? Hyperconjugation. That is why. So at low temperatures, when 1,4 transition state could not be formed at all, 1,4 not formed. 1,2 is the sole product, major product, and at low temperature reaction will be irreversible also. So 1,2 product having less energy barrier of transition state will be formed faster and thus is called kinetically controlled product, because kinetics, that is rate of reaction, is the factor which is supporting its formation, and 1,2 product is formed as major. Right? This same thing I have detailed here again, but the idea is same. And I have exemplified with HBr. So HBr at 40 degrees centigrade is the conversion temperature at which reaction becomes reversible. Okay, at 40 degrees centigrade, this 1,2 product form goes back to this carbocation. 1,4 also goes back to this. When the situation is reversible, the one which is thermodynamically controlled product will ultimately be major. So 1,4 product will become major. For HCl, this temperature is 45. At higher temperature, the second step becomes reversible. That is, the product form comes back to the carbocation. And thus, gradually 1,4 product becomes the major product due to their stability. And they are called thermodynamically controlled product, which is TC product. So what about KC product? Transition state is more stable, faster to form, but product is less stable. TC, transition state is less stable, slower to form, but the product is more stable. Now, as far as exams are concerned, if question mentions temperature is 40 degrees centigrade or above, then the answer is TC for single correct. Multi-correct, you answer both KC, TC. If the question mentions temperature is below 40 degree, then you answer KC products, kinetic control. If there is no question, if question do not mention anything about temperature, then also TC product as major product. Okay, then you answer TC product as major product. Clear? If there is no mention of temperature. See, with HCl at 60 degree minus 60, we have 1,2 products as 75% and 1,4 only 20-25. HBr with 0 degree, we got 71% 1,2 product. From 40, you have 85% of 1,4 product. Right? At minus 80, you have 80% of 1,2 products. So clearly, from 40, you can have a shift from 1,2 to 1,4. At higher temperature, 1,2 product also start getting converted to 1,4. So now how the questions are to be addressed, how the questions to be done for this 1,2, 1,4 thing. So like this, you form a carbocation, a stable one. Do not form this one. Okay, take the stable because this is forming, see, both sides are 2 degree. Here 1 degree and 2 degree. Now whether I take this way, 1,2 product or 1,4 product, I have the same thing formed. If transition state of both 1,2 and 1,4 products are of same energy, see, there is no difference in the two energy, and the stability of both 1,2 and 1,4 product is same, then 1,2 is both KC and TC. Then whatever, see, there is no difference between these two. Then you call where this 1,2 is the major. This is due to something called proximity effect. Like bromine is closer to the second position rather than to the fourth position. So there is a more probable possibility that bromine will attack at the second position. This is both. This is kinetic control also and thermodynamic control also. There is no point in having a difference because the barrier for the involved transition state is same. The product is same. That is why. Okay, but if see there is some difference like this, how to answer? You take this. Now see there is a difference in 1,2 and 1,4. Right? Again there is an important point. 1,2, if I attack here, I am getting this. And my alkene is more hyperconjugated. If I attack here, my alkene is less hyperconjugated. So KC product is 4, though it is this time 1,4. And TC product is 1,2 only. See, this is 1,2. Is that absolutely clear? This time 2 is my more stable carbocation resonance structure rather than this. So there is nothing like always 1,2 or 1,4 KCTC fixing. Go for structure to structure, molecule to molecule. Now come to this. Again, I'll take the same thing. I'll take the CH plus addition. This is a carbocation, so this is definitely more stable. And I form a product, alkene, 3-alpha-H I got. If I take a resonance, I have this carbocation, which is less stable, but my alkene is more stable. So again, my 1,4 product is TC product. That is how you will take. Same thing you will practice here. Same logic. Form a carbocation and compare. Okay. One equivalent, it means that you have to take 1,2 versus 1,4. I have added so many more questions. You can solve them more. And it is not limited to 1,2, 1,4. You can have 1,6 also. Like what I want to say is, for example, if I am asked, say 2, 3, and they say HBr 1 equivalent, then why not? You can have bromine, right? And H here. This type of attack is possible. This is a 1,6. So basically, jitna bhi resonance ho sakta, that is possible. It is not just 1,2 or 1,4. Conjugation can take you far. Jitna far, utna aap apna answer add kar sakte. Clear? So this all you can practice. 1,2 and 1,4 addition products are called allylic rearrangement. They are also called rearranged products. Okay, so that is a example of a rearrangement. Similar thing we will study in carbonyls also, but that we'll study in carbonyls. No need to study now, but yes, this is applicable in carbonyls also. Still here, it was for alkenes. Is that absolutely okay? So that brings us to the closure of alkenes and alkynes discussion. Yes, I forgot to tell you one more. Please go through this entire reading and the conversions, everything. Okay, questions could be framed from anywhere, like structure of benzene is fine, but in the end, there are always uses and the carcinogenic effect things also in the end. Please read this NCRT in detail, this carcinogenic and toxicity. They could also formulate questions from here for mains at least. PTM will be there, na? So please read all these questions, all this theory clearly and with focus, marking kar karke. Revise the IUPAC names. Okay, and do all this. So now only those who have doubts, they can stay back and others can definitely leave. Those who have any doubts, please stay back, raise your hands, and same with the way we do daily, others can leave. If anyone has any doubt, please raise your hand. Okay, Ashish.
Ma'am,
Yes, Ashish.
ma'am, how to differentiate even if the question is asked based on E1 or E2? How to predict the
Okay.
products? Yeah.
And how to predict the mechanism,
Okay.
right?
Yeah. How to
So,
proceed the question? If the yes, ma'am.
yes.
That
So
is me.
actually, Ashish, for E1 and E2, if we say comparison, if we draw, let us draw. Please mute yourself and then again you can unmute so that I
Okay.
can discuss. If we say, or if we go for the differences. Okay, so first, both have the same order. 3 degree better than 2 degree better than 1 degree for different alkyl halides, RL. And a same iska bhi same ही order है, 2 degree then 1 degree. Relative reactivity order. So this is not helping us to decide. Second, in E1, C plus formed. So there is no involvement of the base in E1. Anna? Here, base is involved in elimination. So what does that have impact? What does that changes about the question? If base used in reaction, or I can say question, is weak. Okay, because you have to remove H plus from that alcohol or alkyl halide, so you have to have a base in the medium. Then even if base used is strong in the elimination, or in the same thing, same way I write, in reaction or question, then hold on a second. Then if the base used in the structure, if the base used is strong in the reaction or question, then go for E2. Now let me exemplify it further. What is there in my mind and why I'm saying this? Let me clear it. So, for example, let us take comparative set of alkyl halide I'm talking. Okay. So if I have CH3, CH2, CHX, CH3. If I'm given, say, H2, sorry, some H2O or heat, base is very poor, na? It is a case of solvolysis. So major is alcohol. But if some elimination will take place, then it will be a combination of E1, SN1. Instead, if I am given alcoholic NaOH, now my base is OH minus, which is further less solvated. So you have E2. Is that clear? Does that make sense broadly? Right? If I'm given aqueous NaOH, now see my base is there, but is not sufficiently, or not heat, or nothing is given. Whereas here I give heat. Nothing is mentioned. Then I'll rather go by SN1 or SN2. SN1 for 3 degree alkyl halide, and 1 degree and 2 degree ke liye I will take SN2. Similarly, you can formulate if the base is usually weak, then you go E1. Otherwise, you take E2. If I talk of overall E1 and E2 composition reactions, then it is found that almost 80% of eliminations are E2. Hardly 20% or less are E1. Why? Because E1, it means the base is weak. And it means that SN1 is always behind there. So SN1 will dominate over E1. Now, in case of E2, yes, SN2 may compete, but the order of SN2, this is the order of E2. If I talk of order of SN2, it is 1 degree greater than 2 degree greater than 3 degree. If here I talk order of SN1, it is 3 degree greater than 2 degree greater than 1 degree. See the same order. Whereas here it is complementary, or either I should say opposing. SN2 has 1 degree best, so E2 has 1 degree as worst. So they are the opposite in spectrum, whereas this is same. So wherever I form a 3 degree carbcation, it will go preferably thermodynamical preference for SN1 rather than elimination. So E1 is a very less possible chance. Is that absolutely okay, Ashish? Does this help? Yes, Ashish, tell.
Oh, okay, ma'am. Thank you.
Okay. Anything else, anyone? Yes, I think I have Shiva. Just wait, Shiva. Let me allow you to unmute. Yes, Shiva, please tell.
Ma'am, like what will happen when we take 3-degree alkyl halide into a Woods reaction?
3-degree alkyl halide in a Woods reaction, did I hear?
Yes, ma'am.
Shiva, as far as I'll answer this in two parts. I'll answer this question in two parts. Now, why two parts? Let me tell you. Ideally and given in NCRT. First, ideally, if I take a 3-degree alkyl halide in Woods reaction, okay, so what will happen? As it is a 3-degree, whether I go for a radical or go for an ionic mechanism, 3-degree के केस में alkene is major by disproportionation. Okay, is major by disproportionation in radical mechanism, or if you take ionic, so by E2 in ionic mechanism. Okay, this is what ideally I am expecting. But NCRT has no such comment mentioned. NCRT took normal woods for 3-degree also. Okay, I'll show you. There are questions. Let me share the screen. Woods was given in 11th, na, Shiva? Am I right? Did I share the screen or not? Let me share this. It is visible now, na? So I want to show you something. It was in 11th or in 12th NCRT. One subjective question is there in that pink box where they have considered 3-degree alkyl halide also giving very good normal woods. That is why following the NCRT, we should continue with woods if they ask. Let me reach. This is alkynes part. Alkanes, Ajay, then I'll stop. Just wait, Shiva. Aromatization. Have I reached? Yes, reactions I have reached. There was one pink box somewhere, whether it was in 12th or in 11th, but that is alarming where they have used. Wait, from unsaturated, from alkyl halides, Woods reaction. Not here. Give me a second, Shiva. 11th, 12th. 12th alkyl halide is first chapter. Na? Is this visible, bache? Give me a thumbs up, Shiva, if this is visible. Okay. Let me go down. Let me go down. There was a question which was very important to be noted regarding how they take in NCRT, because that is the outline how they will consider if there will be disputes. And that took my attention very clearly that they are not following all these big books mechanism. Okay, they are following direct NCRT, their own thing. It was a pink box. I remember it very clearly. But I was not ready for this question. Otherwise, I would have cut it and shown here only. Physical properties. Now reactions will start. Reactions. So first they are talking of nucleophilic substitutions. Fine. I am not able to locate the question. It was very important. They took, Shiva, directly 2-methyl, 2-chloropropane, and they considered woods, and they formed the product and continued. It was ABCD type big sequential question in a pink box. Or if you allow me, tomorrow I'll find that question and will share in this notes. Okay, Shiva. So that is how you should take. You split that thing into two portions. One is ideally, and one is what is given in NCRT. Okay. And if you have a similar call to be taken for, I got it here, not a pink box. That was a confusion. Shiva, is this appearing to you? Is my this thing I want to say? See, identify A, B, C, D, E, F, R dash. They are taking an alkyl halide and taking this. If you'll solve this, na, you'll find it is 2-methyl 2-halo thing they are taking. This is what I was like. Oh, so NCRT has taken even for 3-degree Wood's reaction as a normal coupling reaction, Shiva. Okay, so if it appears in mains or something, go for this particularly. If they ask very clear comparative question, then only you talk. Otherwise, NCRT is not following that 3-degree better than this thing. The way I answered the question. Is that okay? Anything else? Let me come back to this. And yes, Shiva, if there is anything else, please.
Ma'am, what will happen if we take the same thing, the 3-degree, in the Kolb's electrolysis, CO minus Na plus?
Same as Woods. Same as Woods, I mean that you will have a disproportionation because a 3-degree radical will not give a proper coupling due to steric factors, and you will have a elimination to alkene, that disproportionation thing. Okay, Shiva?
Ma'am, and one more thing, one small thing.
Yeah, tell.
And will alkenes show free radical substitutions other than chlorine, ma'am?
Alkenes, you said, Shiva?
Alkanes.
Alkane, A-N-E.
Yes, ma'am, alkanes.
Ideally, yes, they have more because if you see, there are two more reactions. One is the nitration of alkanes, one is the sulfonation of alkanes. Okay.
Okay, ma'am.
Now, in case of sulfonation of alkanes, it is expected to be carbocatonic. So they are not very logical, but they are there and are expected. This is expected to react like this. And we have RSO3H to be formed with highly concentrated H2SO4 if we react. Whereas
Okay.
with RH plus HNO3, HNO2 I'll write, and when I write this reaction is expected to be radical and very uncontrolled radical. You get RNO2, but if you have the size of R defined, na, it is very, very mixed product thing. For example, if I take propane and I treat it with conc HNO3 and this whole radical thing, it is no fixed thing where it will go. Like I will have this product. Like halogenation, you have some major minor composition. Here, no. And to add to the problem, it also shows entire splitting of carbon thing also. Like you will have this also. So I took the smallest possible to make my example with 4 products. If I'll go for 4 carbon and further, you can imagine what mixture I will get. But yes, as your question was, are there any other radical substitutions? The answer is yes.
Okay, ma'am.
Okay.
Thank you, ma'am.
Okay, beta. Anyone else? That was Shiva. Anyone else? Okay, I have Feisty. I unmuted you. Yes, tell.
Ma'am, I have a doubt from isomerism.
Yeah,
If
tell.
in the question we have a product which is optically active that forms optically active isomers, then how do we calculate number of fractions?
The only thing you should take care is if they are structural isomers. Okay, I have taken a notice that you asked optical isomer. I'm
Yes.
answering it from 0 base. So structural isomer, take into different fractions. Take into different fractions because I think your name was Shivangi, na, Feisty?
Shubhangi, ma'am.
Shubhangi. So Shubhangi, structural isomers have different boiling point because the fractional distillation is based on difference in boiling point. So structural isomers, different boiling point, take into different fractions. That is approach number 1. If we are talking of different GI, then they are diastereomers.
Yes, so 2 fractions.
Take into different fractions. Clear. If I am talking of optical isomers, now optical isomers could be, say, a combination of meso, could be a combination of 2 enantios, could be a combination of, say, other diastereo combinations, stereo combinations. Enantios have same boiling point. So enantiomeric pair will go in same fraction. Okay, but if one enantio and other, like one is this and other is a isomer with which it is forming a diastereo, so it will have different boiling point. Is my screen shared, Shubhangi?
Yes, ma'am. Yes, ma'am.
Okay. Different boiling point. So will go to different fraction. Meso, if taken, always have a diastereomeric relationship with any of these. So will go to different fraction. Only thing which will go to same fraction is if they are having isomeric relationship with each other. Okay, let me add a little more to this. For example, if I am said tartaric acid, I want to have a little bigger thing. So let us not have a tartaric acid. Something different I want to take. Say I'll take some cycle. Okay, so I have chlorine and say bromine. I have chlorine and bromine. So these are enantiomer. So one fraction. But if I have chlorine and bromine, if I am asked for these are diastereo. So different fraction. Clear? Bromine. And if I am taken chlorine and bromine, this is again enantiomer. So same fraction. So total, how many fractions if out of these 4 given? Right? एक second. This is not, this should not be dash. It should be veg only, na? Because enantiomer I am preparing.
Yes.
Right? So if I'm asked total for these 4 only I am commenting, I'll have 2 fractions. One of this enantiomeric pair and one of this enantiomeric pair.
Ma'am, don't we count diastereomers too as 2 different fractions?
Yes, we will. But they are already now in 2 different fractions. Na?
Okay, right.
This is in one fraction and this is in another. So any pair of diastereomer which is there is practically in 2 different sections only. Na?
Okay, ma'am.
Is that clear? So this outline you remember. You can take a screenshot. Okay.
Okay, thank you, ma'am.
Thank you, Bache.